Once we are done with the Laplace transform, we have to take the system back into the time domain, and for the time domain signal we have to convert frequency domain system or signal into a time domain signal by using inverse Laplace transforms. And this will be included in lecture number 3. So from hence onwards we'll be using methods to translate Laplace domain function back into the time domain function, which is the procedure is known as inverse Laplace transforms. And the majority of the case we'll be doing partial fractions and expansion of partial fractions, so that we can translate any type of system into any known form of the system, and the known form can be translated back into the time domain by using tabular forms. And the tables that we have studied so far contained delta t, u of t, it contained higher powers of t, it contained exponentials, e raised to power minus alpha t type of functions, and it also contains sinusoidals. The product of few functions are also discussed, something like t times e raised to power alpha t, and derivatives and integrals of some functions are also discussed in the previous lecture. So from now onwards we'll be talking about inverse Laplace transforms. To find inverse Laplace transforms of a complicated function, we can convert the function to a sum of simpler terms for each, for which we know the Laplace transform of each term. Let's say the function f of s, which is in frequency domain, can be decomposed into n of s divided by d of s, where numerator and denominator are represented by n of s and d of s respectively. There could be many cases. First case could be that the roots of the denominator of f of s are real and distinct. For another case, case number 2, the roots of the denominator of f of s are real and repeated. And the third case is roots of the denominator are complex or imaginary. So these three cases will be dealt in partial fractions, and all of these three cases will be dealt in the next lectures. Okay, for case 1, roots of the denominator of f of s are real and distinct. If the order of n of s is lesser than the order of d of s, means numerator has lesser order and denominator has more order, then n of s is equivalent n of s divided by d of s is equivalent to n of s divided by s plus p1, s plus p2 into s plus p3, and so on and so forth till s plus pn. They can be subdivided into a parallel system, something like k1 divided by s plus p1 plus k2 divided by s plus p2 plus k3 divided by s plus p3, and so on and so forth. Thus, if we want to know the km, which is a generic any type of coefficient, then we will multiply the above equation by s plus p1 and pm, and the remaining transfer function will become s plus pm is equivalent to f of s times f of s is equivalent to s of pm times ns divided by s plus p1, s plus p2, s plus p3, and going on till s plus pm. You may see that s plus pm factor on both sides will be cancelled out, and we'll have the transfer function which is without s plus pm. Note that the same mth coefficient, which is km, is to be found out. So the transfer function is s plus pm times k1 divided by s plus p1 plus s plus pm times k2 divided by s plus p2, and so on and so forth, plus km Now this mth term is without having any pole in it. We may see that the km is the single coefficient which is without having any type of pole. So the for the values of having k raised to power m, we may proceed in this manner. This is the first step that will multiply the whatever is the denominator of mth coefficient, will multiply it with f of s, and remaining terms will be represented. So once we have a product of s plus pm with f of s, we may proceed in a way that will substitute s is equal to minus p m in the above equation, and then we can find out the mth coefficient, and the mth coefficient can be found out in the equation which is represented at the end of the slide. So s plus pm will be cancelled out from the transfer function, and the remaining transfer function will be without s plus pm term, and we can find out the values of km. Please note it that if we make it present s plus pm and try to find out the mth coefficient or mth constant, by substituting s is equal to minus pm, it will become infinity. So we'll have to reduce it from the transfer function by making product with the s plus pm terms. Another example for a solution of differential equation, from taking them from time domain into a Laplace domain and then solving it in a Laplace domain and back converting it into a time domain, is given in this slide. So the problem is that given the following differential equation, solve for y of t if all initial conditions equivalent to 0 use the Laplace transforms. So let's say if this is the differential equation, d2y divided by dt square plus 12dy divided by dt d by dt of y plus 32y is equivalent to 32 u of t, where u of t is unit step function. The solution would be easier to find out in the frequency domain rather than solving it in time domain. So we'll take Laplace transform, and the term comes out to be s square d divide. S square is because of double derivative of time, and y of s is because of y of t, and we have translated into s domain. So that's why derivative is going to be converted into simple multiplication of s square, and it will become a linear algebraic equation. Similarly, 12 d by dt of y will convert as 12 times s y of s, where single derivative is converted to s times whatever is y of s, plus 32 y of s is equivalent to 32, which is constant, and the Laplace transform of u of t is 1 over s. So if we combine y of s from left hand side of this equation, it will become 32 divided by s times s square plus 12 s plus 32, and we can factorize this equation s square plus 12s plus 32 because it's quadratic equation. We can find out the roots of this equation by simply applying quadratic formula, which is plus minus b square divided by 2 b square minus 4ac divided by 2a, and we know that whatever is the formula. So it's 32 divided by s, and another factor is s plus 4, another factor is s plus 8, and we can factorize it. Now the solution is of y of s, which is the output y of s. It's present. There is only need of translating this y of s back into the time domain, and we'll have y of t, which is the solution. So we need to convert back this transfer function into time domain by taking partial fractions. So let's take three coefficients k1, k2, k3. k1 divided by s1 would be the first term that will be added into the system to make a complete y of s, plus k2 divided by s is second term, plus k3 divided by s plus 8 is the third term. And there is a need to find out k1, k2 and k3. If we find out k1, k2 and k3 we can translate this cascade system into its parallel equivalent circuit or parallel system, and that will be done in the next slide. So in this equation, in this transfer function, we need to find out k1, k2 and k3. Note that k1 has denominator as simple s, so it will only be present at s is equivalent to 0. So let's multiply the whole transfer function with s, and s will be eliminated from the transfer function. It is just 32 divided by s plus 4 times s plus 8, and we'll evaluate this function at s is equal to 0, and that will give the value of the coefficient, which is equivalent to k is equivalent to k1 is equivalent to 1. While for another function k2, we'll multiply all transfer function with s plus 4, because the term k2 had denominator equivalent to s plus 4. So we'll just eliminate that from transfer function by multiplying the term s plus 4, and then the 32 divided by s into s plus 8 will be the remaining transfer function, and we'll evaluate it at s is equal to minus 4, because s plus 4 is going to be 0 at s plus 4 going to be 0 at s is equal to minus 4. So we'll evaluate it at s is equal to minus 4, and the answer comes out to be minus 2. Similarly, coefficient k3 can be evaluated by taking product of s plus 8 with the previous transfer function, and the s plus 8 terms is eliminated from the transfer function, and it is 32 divided by s into s plus 4, and we'll evaluate this transfer function at s is equal to minus 8, and the value that we'll get is equivalent to 1. So k1 is equal to 1, k2 is equal to minus 2, and k3 is equal to 1. We'll substitute back in the previous equation. We'll have y of s is equal to 1 over s minus 2 divided by s plus 4 plus 1 over s plus 8. And we can now take the Laplace inverse and take this transfer function, which is in s domain, back into the time domain, and y of t would be 1, because 1 over s is going to be translated as 1 in time domain, minus 2 divided by s plus 4, because s plus 4 is just translation in time domain. It will change into rotation in time domain. S plus 4 is translation in frequency domain, so it will change into rotation in time domain by e raised to the power minus 4t, and that 2 is the constant which is appearing same as in the above equation, plus 1 over s plus 8. So this s plus 8 is again a translation in time domain that will again change into rotation in s plus 8 is translation in s domain, and that will change into rotation in time domain. It will become e raised to the power minus 8t, and there is no coefficient because 1 is the amplitude, so that 1 will be appearing here, and all that is taken product with the u of t. And u of t is just showing that the transfer function is only causal, and it is only existing after t is equivalent to 0. So that u of t is only representing that part. So the transfer function y of t is equivalent to 1 over minus 2 e raised to the power minus 4t plus e raised to the power minus 8t. So this equation states that some of the parts are steady state and some of the parts are transient. So steady state parts are something like is equivalent to 1, and steady state and the transient parts are e raised to the power minus 4t plus e raised to the power minus 4 minus 8t. These are transient parts, and they will disappear after some amount of time. So here we have equation in time domain, which is the response, unit step response of the system. Similarly, we will have different other examples present in this lecture, which will be continued after this slide. Similarly, for repeated roots, and if they are real as well, then we'll apply the following procedure to find out the partial fractions and convert the cascaded system into its parallel equivalent model. N of s divided by d of s, which is a polynomial divided by polynomial, could be written down as n of s divided by s plus p1 raised to the power r, where r is the rth root. Let's say r value is 3, then it's third root, and if r is equivalent to 2, it's the second root, plus s plus p2 times and so on, and s plus pn. So here we have s plus p2 to s plus pn. Everything is real and distinct root, and non-repeating roots, while only s plus p1 raised to the power r are rth repeated roots. So we'll do partial fraction something like that. K1 divided by s plus p1 raised to the power r plus k2 divided by s plus p1 raised to the power r minus 1, and it just goes on to kr divided by s plus p1 plus kr plus 1 divided by s plus p2, and so on and so forth till kn. Similarly, if we multiply the first term by s plus the whole transfer function by s plus p1 raised to the power r, we can solve for the k1 for s is equal to minus p1. But for the second coefficients like s plus for k2 and k3, k4 till kr, we need to follow certain procedure which is adapted in the next slide. So first is finding out the value of k1. So we'll multiply the whole transfer function with s plus p1 raised to the power r, and remaining means that s plus p1 raised to the power r will be eliminated from the transfer function, and that transfer function which is now obtained by eliminating the factor s plus p1 raised to the power r will be evaluated for s is equal to minus p1, and we'll have the transfer function of will have the coefficient k1. Similarly, for the second repeated root like s plus p1 raised to the power r minus 1 to k raised to kr will adopt the following procedure, which is presented in the next slide. Okay, this one is for the for finding out the values of k2, k3, k4 and till kr. Don't worry about the difficulties of equations because it can only be representing in sometimes of horrible terms, otherwise it's simpler. And with the help of some examples, it will be quite clear to find out the values of repeated and non-repeated roots. So we can solve for the k2 if we differentiate f1 of s with respect to s and let s approaches to minus p1. So it's the second root, so we'll derivate it first time. Subsequent differentiations allows to find out k3 through kr with the general expression as k. The general expression is given in the bottom, and ki is equivalent to 1 over I minus 1 factorial divided by d raised to the power I minus 1 f1 of s, and it's the I minus 1th derivative, and that whole term is evaluated for s is equal to minus p1. So for the repeated roots, everything is evaluated for for s is equal to minus p1, but the only difference is that we'll differentiate it 1 time, 2 time or 3 time if we are trying to find out the values of k2, k3 and k4. So like I said earlier, that a few examples will be presented in order to make these things clear, that how we'll find out for the values of non-repeating roots. So here is the example of finding out complex or imaginary roots, and definitely they will be in the terms of in the second order term. So n of s divided by d of s, which is total transfer function, can be written down as n of s divided by s plus p1, where s plus p1 is the non-complex or real root, while s square plus as plus b is the factor which is presenting a complex or imaginary root. So if these are the complex or imaginary roots, they will be written down as k2s plus k3 divided by 2 plus as plus b. In general, if we have a polynomial of order 2, we'll have a polynomial of order first order polynomial at the numerator, and if we have a third order polynomial which is complex, so we'll have second order polynomial at the top, and so on and so forth. We can find out the values of these coefficients by let's say k1 will be evaluated like earlier, will eliminate the transfer function, or will multiply s plus p1 to the transfer function. So s plus p1 factor will be removed from the transfer function, and hold that whatever is remaining is evaluated for s is equal to minus p1, and whatever the value of we obtained will be allocated to k1. While for k2 and k3 we'll adopt other procedures, and these procedures are written or will be eliminated, highlighted in the next slide. So the coefficient k2 and k3 are found through the balancing of coefficients of equation after clearing fractions. So let's say if k2 s plus k3 divided by s plus 2 plus s square plus as plus b is put in the form of a times s plus a plus b omega divided by s plus a whole square plus omega square, means it will be following something like cos or sine, and we can obtain the factor in terms of sinusoidals, cos or sine, whichever is closer in the form that will be adopted. And the values of k2 and k3 are evaluated using comparing coefficients. So here it is in the form of s plus b omega divided by s plus a whole square plus omega square. So the first term relates to cos, while the second term omega divided by s plus a square plus omega square will refers as sine. But we know that translation in s domain will convert into rotation in time domain. So e raised to power minus alpha t, which is rotational factor, and the same factor is translated in the s domain. So a e raised to power minus alpha t cos omega t plus b e raised to power minus alpha t sin omega t is the solution for time in time domain, while the factors a divided by s plus a plus b omega divided by s plus a whole square plus omega square is the factor in terms of Laplace domain. In the coming slides, we'll present some of the examples to elaborate how we can take partial fractions and how we can convert repeated, non-repeated, and complex roots. As I said earlier in the previous slide, that inverse Laplace transforms can be understood with lot of different examples. So let's take the example that Laplace of f of t is equivalent to f of s. Then the inverse Laplace transform of f of s is generally Laplace inverse of f of s is equivalent to f of t. So f of t and f of s are Laplace pairs. We'll sometimes use this notation that f of s and f of t are Laplace pairs. The inverse Laplace inverse is a linear operator, so it will be operated on both of the f of s and plus g of s separately, because linear operators can distribute independently on f of s and independently on g of s. Similarly, scaling property also holds. Similarly, distributive property also holds, and commutative property also holds for a linear operation. So as Laplace and inverse Laplace are linear operations, so everything is commutative, associative, and distributed as well. So let's take example where u of s, general transfer function, is equivalent to 1 over s cube plus 6 over s square plus 4. And we want to find out the Laplace inverse of, or we want to have a solution in time domain. So how we can proceed? We'll take Laplace inverse. So u of s, which is a general transfer function in s domain, will be converted into u of t by applying Laplace inverse. Now the u of t will be in time domain, and that will be 1 by 2 Laplace inverse of 2 by s cube. And we know that 2 by s cube, the answer is t square divided by 2. Here it's written by mistake, it's written s square by 2, but it's actually t square divided by 2. And the second factor is 3 Laplace inverse 2 by s square plus 4. as we know that 6 can be distributed by 3 times 2, so this 2 is needed because we want to have a function something like omega square, so s square plus omega square. Well, omega square is equivalent to 4, so omega is equivalent to 2. On the top we must have the factor of 2, so that's why we separate out 6 factor into 3 times 2, and 3 is taken as common while 2 is remaining inside the function of Laplace inverse. So now it is typically in the form of omega divided by s square plus omega square, where this typical function refers to as sine of 2t, and 3 is constant, so we have the total Laplace inverse or u of t function as t square divided by 2 plus 3 times sine 2t. Here we have another example of non-repeating and repeating roots, and we want to find out the Laplace inverse of, let's say, x of s, where x of s is transfer function. It is 1 over s plus 1 raised to the power 4, means 4 it is 4th order repeated roots, and plus s minus 3 divided by s minus 3 whole square plus 6, where s minus 3 looks like translation in s domain. Obviously that translation in s domain will change into rotation in time domain. So e raised power minus e raised power plus 3t will be expected in the time domain function. So let's just take the transfer function of t or t square or t cube. We know that t cube is going to be translated as 1 over s raised to the power 4 with some coefficient, and that coefficient is 6, but 6 is not present, so we'll multiply and divide it with the 6, and we'll have Laplace inverse of 1 over s plus 1 raised to the power 4 as t cube divided by 6. But plus 1 factor is actually translation in s domain that will change into rotation in time domain. So the first term 1 over s plus 1 raised to the power 4 will translate into e raised power minus t times t cube divided by 6, while the second term s minus 3 divided by s minus 3 square plus 6, again here we have something like s divided by s square plus omega square, but that omega square, the value of omega square is not present, so we'll take multiplication and division accordingly, and we'll have Laplace inverse in terms of e raised power minus 3t cos 6 under root times t, where 6 under root comes out to be as omega. Please note that 6 in this factor is actually 6 under root square, which is omega square, so omega comes out to be 6 under root. So this way we can find out the values of Laplace inverse of this transfer function, this type of transfer function. So here we have another example of translating a complex root into time domain. Let's say g of s is equivalent to s times s square plus 4s plus 5 raised to the power minus 1, means s divided by s square plus 4s plus 5 is the transfer function, and we want to have inverse Laplace of g of s. Whatever comes out to be, it will be g of t, because t is in time domain, and Laplace inverse of s over s square plus 4s plus 5, we need to find it out. We may change it in terms of completing roots, that will do s plus 1 whole square plus 1. This will become the factor which needs to be translated back into the time domain, but if you think closely, we need to have s plus 2 in the denominator, then we need to have s plus 2 in the numerator. So let's add plus 2 on the top and subtract minus 2. So in order to have compensation of +2 and -2. But -2 will have the same denominator. Again, the same denominator is 2 divided by s plus 2 whole square plus 1. We need to find out the Laplace inverse of that as well. So s plus 2 shows that it is something like a cos, a factor something like a cos, and 1 states that 1 is omega square. So omega will remain the same. Omega will be 1. While s plus 2 states that translation in s domain will change into rotation in time domain. Means we need to have factor something like e raised to power minus 2t in the time domain, and we have e raised to power minus 2t cos of t minus 2 e raised to power minus 2t sine of t. In this way we can take transfer function of non-repeating complex root, and this root is represented in the example, and we have done successful transformation of g of s in terms of g of t. Let's take few more examples of f of s. There is usually more than one way to invert the Laplace transform. For example, let f of s is equal to s square plus 4s minus raised to the power minus 1. You could compute the inverse transformation of this function by completing the square. So let's say f of t is equivalent to Laplace inverse of 1 over s square plus 4s. So let's take completing the square. It will be having something like 1 over s plus 2 whole square minus 4. Now this s plus 2 whole square can be converted back into can be converted back into the time domain, and the solution is 1 over 2 e raised to power minus 2t sine hyperbolic 2t. The other way could be that you could also do fraction composition, like 1 over s can be separately compensated out, and the values of 1 over s plus 4 can be separately compensated out or transformed separately. So if we compare the if you do the partial fractions and try to find out the values of 1 over coefficients of k1 and k2, it comes out to be 1 and 1 and minus 1. So we'll take the translation as 1 over 4s, and translation of 1 over 4s comes out to be 1 over 4 times ut, because 1 over 4s is 1 over s is just u of t, and 1 over 4 is just a number that's a multiplier or coefficient, so it can be taken out, and it is just 1 over 4. And 1 over s plus 4 is a translation in time domain, in frequency domain, that will change into rotation in time domain, and rotation in time domain is 1 over 4 e raised to power minus 4t. So hence we have the solution of 1 over 4 minus 1 over 4 e raised to power minus 4t. There is no need to translate this transfer function into a sine hyperbolic function, because we successfully converted a frequency domain signal into a time domain signal. This could be treated as signal or a system, both, because we don't know what is f of t, but we don't know what is f of s, so we cannot say whether it's a signal or whether it's a system. So we have final solution as 1 over 4 minus 1 over 4 e raised to power minus 4t. That's enough to translate into time domain. There is no need to convert it into sine hyperbolic or cos hyperbolic or tan hyperbolic functions. So as I said earlier that in the previous slide, that Laplace inverse can be found out in various different ways. So looking at this transfer function, which is q of s, it is equivalent to 3s divided by square plus 1 whole square, can be converted into time domain in many ways. One way could be that we can take 3 as a common number or a fraction or a multiplier or a coefficient, we can take it outside the equation, and rest of them can be done by partial fractions, and but there is a less tedious way. Note that q of s is equivalent to 3 by 2 derivative of s with respect to s, 1 over s square plus 1 whole square, because when we do derivative of 1 over s square plus 1, it will be 1 over s square plus 1 whole square. So realizing that we have a derivative term, we can change it into a derivative way, and derivative in s domain will change into multiplication of t in time domain. Likewise, if we have a multiplication with s, it will be changed into derivative in time domain. So we have d by ds derivative in terms of s domain that will be changing into multiplication with t in time domain. So we have 3 by 2 Laplace inverse of derivative of 1 over s square plus 1, and the answer is 1 over s square plus 1 is just sine omega t. Omega is equal to 1 and it's sine t, and the sine t will be multiplied with t, because derivative will change, derivative with respect to s will change into multiplication of t. So we have got 3 by 2 as a factor. Now where is the negative sign gone? Negative sign gone because of another negative sign will appear while doing derivatives. So that's all from doing further examples, and let's proceed afterwards. In this slide we have a few electrical networks like capacitor, resistor, inductor. So the inductor will have a voltage current equation as Vc is equal to 1 over C I tau d tau, integration from 0 to infinity, and current equation is It is equal to C dV by dt, while voltage and charge equation is Vt is equal to 1 over C Q. That can be translated into S domain, and the impedance is 1 over Cs and admittance is Cs. This can be understood with the help of voltage divided by current, and voltage is V of t. If we apply the Laplace transform, it will be changing into 1 over C, and integration will be changing into multiplication of 1 over S. So that will be changed into 1 over Cs. Similarly, for a resistor, V of t is equivalent to R times I of t. It's a voltage current equation, and if we apply Laplace transform by taking voltage divided by current, that comes out to be voltage divided by current. We need to translate V of t in terms of V of s and It in terms of I of s, and we multiply both. We'll have R. We'll have V of s divided by of s is equivalent to R. The thing that I would like to highlight is that integration is going to change into multiplication with 1 over s. Derivative is going to change with multiplication of s, which can be evident for the capacitor and for the inductor as well. Let's say we have a problem that we want to find out transfer function relating the capacitor voltage V of s to the input voltage V of s for the given circuit. So V of t is applied to the circuit of RLC, and R, L and C are appearing in series. So the transfer function, the output is taken at the capacitor. So the capacitor voltage divided by input voltage will be a transfer function of this network. So let's write down first of all, let's write down equation by applying circuit analysis rules, that L di by dt plus r I of t plus 1 over c integral of 0 to t I of t dt is equivalent to v of t. So if this is the equation, then we can not solve it in time domain, or it's very difficult to solve it in time domain. So why not to take a double derivative in order to convert all that equation either to integral equations or to differential equations. So let's take another derivative in order to remove that integral which is appearing in this equation. L d squared by dt q of t plus r dq by dt. So the current, when it is going to be derivative, it can be translated as q of t plus 1 over c qt is equivalent to v of t. Now we want to write down q of t is equal to c vc, which is voltage across the capacitor with respect to time. So LC is equivalent LC times d by dt whole square vct plus RC v derivative with respect to time of vct plus vc t is equivalent to vt. So here we have this equation which is voltage equation in terms of second order, and the comparison of the voltage of the capacitor is going to be compared with the input voltage v of t. So if somehow we can find out output voltage divided by input voltage, that will be a transfer function, and that will be presenting the whole network, whatever is appearing between output and input. So in next slide we'll try to understand or try to correlate the system which is appearing in between output and input. So here we have equation, second order equation, second order differential equation in time domain, and it's difficult to find out its solution in terms of v of s or v of t. So we can translate it in terms of Laplace transform. So let's apply the definitions of Laplace transforms. Derivative, double derivative will change into multiplication of s square. Single derivative will be changed into multiplication of s. So if it comes out to be LCS square plus RCS plus 1, and VC is taken as common from all of these equations. Note that in differential equations we cannot take common of any type of voltage. We cannot take common VC, but here it's a linear differential equation, we can take common, and it will be equivalent to V of S. So VC divided by V of S, note that VC is the voltage across capacitor divided by V of S. V of S is the input voltage. So output voltage divided by input voltage is equivalent to 1 over LC divided by S square plus R divided by LS plus 1 over LC. Now this transfer function is representing whole of the system which is appearing between output and input. So if we don't have the system and we'll only have the outputs and inputs, we can analyze the system or we can recreate the system. This is the power of Laplace transform, and not only that, we can solve the system and we can find out the voltage across capacitor from this equation by taking V of S is equal to 1, and by taking Laplace inverse of whatever is Vc, we can find out the time domain response of the capacitor. Note that the RLC circuit solution of second order differential equation is difficult in time domain, but it is easier in frequency domain. Similarly, we have a complicated network like presented in figure A. V of t is applied at the input, and Vc of t voltage at the capacitor is taken as an output. Then you may see that it's very difficult to find out transfer function in this way, and the equation that is coming out will be horrible, but we can write them all of these equations directly into Laplace domain, and things will become simpler in time domain. Things will become simpler in frequency domain. So here are the set of equations that we can write down. Still it looks difficult that we have two equations, two independent equations and two independent variables, I1 and I2. It's solvable. We can find out solutions of this equation, but still it looks complex. Mind it, when we have three loops, we only have three mesh or three loops or three nodal equations in the system, which is cascaded again with this system. So when the circuit expands, the equations or writing down the equations is also becoming a problem. But there is a solution of that you may take the help of modern tools, or you may take the transfer function in a cascade. Rather than doing transfer function, finding out the whole transfer function, you may take the transfer function in first loop, and transfer function of first circuit will be fed into the transfer function of the second circuit. So this way you may take cascaded form. That will become simpler. That's all from Laplace inverse and finding out circuits, electrical circuits. You may have mechanical circuits, you may have electromechanical systems, rotationary systems. All of these can be translated in ultimately in terms of differential equations, and finding out solution of differential equation in time domain is difficult. That's why we go for Laplace domain. And finally, having a simpler form in Laplace domain, we can back convert all of the transfer function into time domain, and the solution of time domain can be obtained easily in that way. So that's all for all of the three lectures, and from next week you will be studying some more mathematical modeling on electromechanical systems and so on and so forth.